If I got stuff for you, have stuff for Yeah, my mom. She said, if you're not happy, you don't have to be
All right. So we've talked about even functions and odd functions because our even functions are the ones that have our y-axis symmetry, and our odd functions are the ones that have our origin symmetry. So we kind of squished this in when we were doing our symmetry tests back a couple of sections ago. So there is a way to test both for evenness and oddness in one test. Instead of having to do like our 3 separate tests for symmetry, we can just do one to test for evenness or oddness. It just doesn't tell us if there's any x-axis symmetry. So that one would have to be done separately. So if we want to do this as one test, we can substitute our minus x in for every one of the x values. If we get exactly the same thing we started with, it's even. If we get the opposite of itself, so we have our function times -1, then it's odd. If it's somewhere in between or anything else chaotic, it's neither. So it could be even, it could be odd, it could be neither. And we're going to practice this on a couple of them. So if the wordiness of this is not particularly pleasant, so if our f of minus x is the exact same thing as f of x, we are even. For it to be odd, that would be when our f of minus x is the exact same thing as minus f of x, or minus 1 times f of x. So I'm just going to give us a few minutes to write that down, and then we're going to go and practice this a couple of times. 4 times. Okay. I'm going to change it in 3, 2, 1. All right, so we're going to look at these functions. These two. Oh, yep. Absolutely fine. I'll put it back here for just another minute. Cool. Boop. Yeah, I can almost always put it back. I'm going to guarantee always, because sometimes I hit buttons weird. And things decide to change on me. This cable is rectangle. So these are the functions we're going to look at. We're going to see if they are even, odd, or neither. There we go. Now you're going to power on. So on this first one here, we have our f of x is x to the 4th minus the absolute value of x. So if we substitute the opposite of x in, for both of these, we're going to do our f of minus x. So we're substituting the opposite of x into our x to the 4th, and we're going to substitute the opposite of x into that absolute value.
You can't have absolute value of negative,
An
right?
absolute value cannot equal a negative. But I can put a negative inside an absolute value. Like, what's the absolute value of -2? 2. Absolute value of -7. 7. So we can have a negative inside the absolute value. It's just that it doesn't really change anything. Because when we simplify that, that's 100% going to be the exact same thing as our absolute value of x. You're absolutely right there. What happens when I have minus x being raised to the 4th power? It's just the same thing as x to the 4th. Like, nothing has to change there. Because when we have an even power, the signs don't matter. Just like -2 squared is going to be 4. Same thing as 2 squared would be 4. So 2 to the 4th is 16. So -2 to the 4th is also 16. So it doesn't matter if it's positive or negative. If it's an even power, the negatives don't matter. So is this going to be even, odd, or neither? Even. Because this is exactly what we had as the original, as our f of x. Since our f of minus x exactly equals our f of x, this is indeed even. Meaning it has that y-axis symmetry. Then let's look at this one on the right here. We've got f of x equals x over x squared plus 1. So again, we're going to do this by substituting in that minus x. Every place we have an x. So we're going to have our minus x in the numerator. We're going to have minus x squared plus 1. See what we get when we start to simplify. What happens? So we're noticing in our denominator that minus x being squared is the exact same thing as if we just had our x squared plus 1. And our numerator, is that going to simplify at all? No. So we just have our minus x here. So do we have exactly what we started with, f of x?
No.
No. So we know it's not even. No. I'm not sure what. I think you're thinking negative exponent. This is just negative out in front.
The x terminated or anything.
But I could rewrite this, right? We could rewrite minus x as minus 1 times x. Or in fact, we could have that as minus 1 times x over x squared plus 1. Like, that's the same thing, right? I say that's our, this is a negative 1, that's a times, just because my negative and my times both in a little symbol. Because I could rewrite my minus x as minus 1 times x. And I could same thing as minus 1 times x over this, which means this is minus 1 times f of x. So it's the exact opposite of what we started with. It's negative 1 times what we started with, which means this one is odd. This guy was even. Because this is our negative 1 times f of x. I went this way. I wrote it up. Let's look at another one. We'll look at the one that's on the bottom now. We're going to have f of x equals x plus 6. Same thing. We're going to substitute in our minus x in place of x. So we're going to have our f of minus x. And we're going to substitute in our minus x plus 6. Substituting that minus x in place of every x we have. Our f of minus x. In this case, we just have our minus x plus 6. So is this even? No. This is not exactly what we started with. So it's not f of x. So it's not even. If I factor a minus 1 out, so if we make this minus 1 times, what would we get? X minus 6. So this is still our f of minus x. Is this exactly what we started with? No. X minus 6 is not the same thing as x plus 6. So this does not equal our minus f of x either. So it is also not odd. This is neither. If it equals f of x, we're even. If it equals minus f of x, it's odd. If it doesn't equal either, that's not equal to. Then it's neither. Neither is an absolutely valid answer. So if we get exactly what we started with, it's even. If we get negative 1 times our original function, it's odd. If we get neither, it's neither. Or neither. Questions as it stands right now. I've heard a few whats, but no further question. All right, we're going to do one more like this before we move on to other things. So we've got our f of x equals 2x cubed minus 6x. So we're going to start by doing our f of minus x and substituting the opposite of x in. So this is going to be 2 times our minus x cubed minus 6 times our opposite of x. Start by substituting in our minus x. And then we're going to simplify as much as we can. What happens when we cube a negative value? Do we lose the sign or do we keep the sign? Keep the sign. So if I have 2 times negative x cubed, how could I write that? Negative 2x cubed. It'll be the exact same thing as if I had a positive value. I just made the whole term negative. What about with our minus 6 times minus x? Plus 6x. So we've simplified it down so we don't have any parentheses. Did we get back what we exactly started with?
No.
No. Once we have no parentheses, we check and see this is not exactly the same. So this is definitely not even. This is not exactly equal to f of x. So it is not even. So then to see if it is odd, we're going to factor a minus 1 out. So if I take minus 1 out, what are we left with? 2x cubed minus 6x. Is this piece exactly what we started with? Yes. So this does equal negative 1 times our f of x. Because this is negative 1, this is f of x. So that means this one is, in fact, odd. Okay? So it does several of our symmetry tests all at the same time. Questions on these bits? Okay. The next thing we're going to do is going to be very different. Because we're going to talk about discontinuity. And we have 3 kinds of discontinuities we're going to work with. We'll have jump discontinuities. Yes, dear. You said to the bathroom? Yeah. How would you pass? Oh, back a slide. Yes. Sorry, I thought if you could go to the bathroom. Yeah, no worries. Okay, so we're going to have a jump discontinuity. We're going to have an infinite discontinuity, which is also the same thing as an asymptote. And we will have a removable discontinuity, also called a hole. And we're going to see these in different places, and I'm going to tell you about where we'll see them. And mostly what we're going to do to show these is just kind of sketch them. So, I'm just changing colors real quick for me, just so things are very different. All right, so when we think about a jump discontinuity, what that means is somewhere on my function, I basically get a teleport. So I could have something like this, where I have then an endpoint, and it's going to jump to a different value. It may even jump to a different kind of function.
With the ending dot align.
Yes, a jump discontinuity will line up. So this would be the same x value. It just would have an open circle on one piece and a closed circle on the other to maintain that domain. We will mostly see these in piecewise functions. I'm just going to put that down here. Which we will get into piecewise functions, I think by the end of the week. And that's, you've seen them before, it's just been a minute. That's when we have the like y equals, and they have this thing. Or they'll have like x squared when x is less than -1. Or, and then like 2x minus 4 when x is greater than -1. That kind of vibe. So those are our piecewise functions, and we'll get into those later. I promise we're going to work into them. But they have a jump discontinuity. Think of it like a teleport. I was here, and then boop, jump down there. I'm going to move this little piece so it's out of my way for my infinite asymptote, or my infinite discontinuity. I was just moving that piece out of the way. You don't need to have that thing there, but since I wrote it, I'll leave it there. What an infinite discontinuity is an asymptote, which we've worked with these in rational functions. That's when we usually draw our dotted lines, and we get, no, hang on, changing colors. Like these kind of things. Just changing the angle on that one. Like this. Like these kinds of guys. This asymptote would be our infinite discontinuity. It approaches infinity, is what that's meaning. And we see these mostly in rational functions, like our 1 over x kind of guys. And we'll see these in exponential functions and logarithms.
Is that the one where it's like close to touching the x?
Yes, it's getting obnoxiously close to touching, but then it's going, I'm not touching you, I'm not touching you, I'm not touching you. And it's getting as close as it possibly can because it is the most obnoxious little sibling ever.
Which one of them have two asymptotes?
Like when it has this kind of guy, that would be our rational functions. Like that's like the 1 over x kind of guys. And we're going to have a whole lot of those in chapter 3. We're going to really focus in on those.
Okay, you're right.
I'm going to write it in. Mostly seen in rationals. And then that's like our 1 over x kind of things. Exponentials. Like 2 to the x, that's what we mean by exponential. Or logarithms, which is the inverse of that. So like log of x, or log base 2 of x. Or logs. There are other pieces that have asymptotes, but they're not like super that we see often. And then removable discontinuities, also called whole. That'll be when we have a function, but somewhere somebody stabbed it. like that. So we've got this hole. Somebody came up to my line and just went and stabbed and poked a hole. It may or may not have a different value for that point. It could. They could tell us that it's up there. It's still a function. It would pass my vertical line test because I'd have a closed circle versus an open circle. It's still a removable discontinuity.
Do they have another value?
They do not have to have another value there. If we have another value there, our domain is then still
What's with the
like
dot?
infinite. It could have an alternate value there, which would mean our domain would be two separate pieces. So it's just whether or not we have our domain still being like negative infinity to positive infinity versus two pieces where we have to hop over that piece. It can be either way, where I know that maybe instead of being right there, maybe it's right here. Or maybe this value is actually down here. Or maybe there's no value at all and it just can't be there.
Where are these ones mostly seen?
These are mostly seen in rational functions. This would be when we have something that cancels out top and bottom, or in piecewise functions. So it may or may not have an alternative value. We had these a lot of times in our rational functions when we'd have, like where we could factor our denominator. And we'd have like x plus 5 in the numerator and x plus 5 in the denominator. So they canceled out, except for the place where it caused us a problem. And we had a discontinuity, we had a hole. So these are the three kinds of discontinuities. What we're going to start with right now is we're going to do some sketches of graphs given a description. And we're going to practice kind of looking at these, what they look like, and all that jazz. And if you want graphs, I can get you graphs, but honestly, we're just doing kind of a sketch, so it's not a huge deal. I'm just going to give us a little bit of time because I know some of us are still writing, but it is slowing. All right, so we're going to sketch a function with these discontinuities. So I want to show a function that has an infinite discontinuity at -4, a jump discontinuity at 3, and a removable discontinuity at 5. The way I'm going to do this, I'm just going to draw myself like my own little table here because it doesn't have to be perfect. We're just doing a sketchy thing here. So if I know I need to have an infinite discontinuity at -4, so 1, 2, 3, 4, here's -4. Ta-da. Infinite discontinuity means I need to have an asymptote right there. So I'm going to have some asymptote here. It's going to be a vertical asymptote. And maybe my function just kind of goes like that. And on this side, it could come down over here and keep going this way. We're going to keep filling more pieces in, so I'm not going to put an arrow. So it could be up there like that. It could be down below like this. We could go all kinds of crazy pants on it. Whatever we want to do. Creative choice. I'm going to go ahead and bring it kind of up like this. Because then our next piece we want to have is we want to have a jump discontinuity when x equals 3. So at 1, 2, 3, I need this to jump somewhere else. So I'm going to put a hole right there. And then I just need it to show up somewhere else at 3. So maybe it pops down here. Valid.
Does it have a closed circle or open circle at the time?
We can have a closed circle and an open circle at the same time. I could have an open circle and an open circle at the same time. I cannot have two closed circles because two closed circles would fail the vertical line test then, and it's no longer a function. We don't want to do a one like this right now because that is a removable discontinuity, not a jump. I need to switch my whole function down to a different place. And it can continue elsewhere. But then I'm going to be careful because I know at 5, we are going to have a removable discontinuity. So when we get to 5, here's where somebody stabs a hole in it. And then I can keep going. So removable discontinuities are where somebody stabs my line. Jump is where it breaks off and goes somewhere else. So it snaps it off and teleports. This is just somebody goes, yeah, and stabs it. Might have to make that noise just happen. Yeah. And the next one's going to be very similar. Like, there's a lot of choices we can make in here. There is so many choices I could make with how we approach this asymptote, what kind of functions we have here. These can be wiggly squiggly. This one could be wiggly squiggly. I'm just kind of making pieces up. It's a sketch. It's a vibe. That's all we can do. So then the next one, if we have a jump discontinuity at -3 and a removable discontinuity at 2, so now we're going to have something over here at 2. 1, 2, 3. Here's -3. So again, it doesn't have to be perfect. We don't know anything else about it aside from the fact that it's going to have a teleport, a jump, at -3. So whatever's going on with this line, when I get to -3, it needs to teleport somewhere else. Maybe it just comes straight down here. And it could still be a horizontal line here. Maybe it just jumped down here. And then when I got to 2, we have a removable discontinuity. It may have a point elsewhere. It may not. Either way, it has a removable discontinuity. It can be removed and placed elsewhere, or it can just be removed and turned into a lava pit, where we got to jump over it.
Wait,
Yes, dear?
what's this one?
This would be if we had a removable, and I just, instead of like throwing it away, it makes a point somewhere else.
Oh, wait. Oh,
Okay?
I wrote -10.
It's all good. It happens. Again, it's still just, we're just kind of going for a butt right here. There's a lot of options that can be taken on these. There's lots of choice, lots of creativity that you can use on those. There's not one particular answer. It's just kind of a vibe. Okay. Questions on these two? Because we're going to work towards getting to be able to graph things like this properly by the end of the probably week. We'll be able to do those. Which means we're going to need to remember how to graph some functions.
Oh, yeah.
And we're going to get one little new thing in here.
Oh, jeez.
So, we're going to be graphing lines, quadratics, absolute values, cubics, square roots, all that kind of stuff. We have seen most of these transformations before. A, same thing, reflecting over the x-axis, vertical stretch or compression. When does A reflect us over the x-axis? If A is negative. So if A is less than 0, it reflects over the x-axis. If we have stretch, vertical stretch, when does that happen? When the value of A is greater than 1. So, or if the absolute value of A is greater than 1. When does A do a vertical compression? If it's between 0 and 1. So if it's a little. So the absolute value of A being less than 1. If A equals 1, that's just kind of the default state. It's no stretch, no compress. So we tend to put it like with the absolute value because that's, whether it's positive or negative, it doesn't really matter. If -2, it is still a vertical stretch. It's just been flipped at the same time. H we've seen before. That's our horizontal shift. So if H shifts us left, what do we know about H then? It's negative, so H would be less than 0. If H shifts us right, our H is going to be greater than 0. Now, I should probably write down our transformation form so we can see that. Think about with our A, and I'm going to put my X minus H plus K, leaving a little bit of space here for a reason. So think about these kinds of guys. We did it with squares, we've done it with absolute values, we've done it with square roots, these kind of things. K does our vertical shift. So it shifts up or down. If K shifts us up, what do we know about its value? It's going to be positive, greater than 0. If K shifts down, it's going to be less than 0. We know it's negative. Now this last one we probably have not seen before, or we might not have seen before. B. That is in a different place in our function. So A is usually multiplied out in front. B would be multiplied inside. So if we were in quadratics, the square would be out here. If we were cubes, it would be out here. If we were our square roots, it would be like this. Yes, I'm just putting that piece up there. So this would be where our power is, whether it's 2, 3, 5, 1/2, whatever. This will be the last page we write, by the way, and we'll start practice with the graphs tomorrow. So I'll have this up for like the rest of the day. Just because I know there's a lot of stuff on here. So B is kind of a new piece. And this is where we would get something that would reflect over our y-axis. So instead of flipping upside down, it does what I call discontinuities. It reflects this way. So it goes this way around our y-axis. So B is weird, but it's very, very similar to A. So it is, again, being multiplied inside. So A is multiplied out in front. B is being multiplied inside.
What's P?
Oh, that's some power, whether it's squared, cubed, if we did our absolute value, if we did our square root, that would be where that function goes for. It's just because this works with just about every function ever. Like everything. And if we had a B, it would be multiplied inside here. So inside. This one doesn't have the B's because this is the algebra 2 version. And you've learned all this. This is algebra 2. And I'm actually going to give you a paper that has all of them on it. Okay, so we're just going to talk through B because B is weird. B will do a reflection over our y-axis. That's reflecting it this way as opposed to going upside down. And that will happen if our B is negative, just like A does. So if B is less than 0, it reflects us over our y-axis. B can also do a stretch or compression. It's just reversed of what A does. Because if our B is bigger than 1, so the value of B greater than 1, it's going to be a compression. It's going to take my graph and it's going to compress it horizontally. So it's going to squish it this way. If my b is smaller than 1, it's going to be a horizontal stretch where it takes my graph and it goes stretching it this way. Yes, dear?
So instead of A multiplying the y, this is going to be multiplying the x.
Mostly, yes. We have to actually multiply it by the reciprocal. I promise we'll get there. It's 1 over b times the x. But yes, other than that, it's exactly the same. So it's affecting our horizontal shift. We will practice with it. And in fact, we're going to do it with parent tables that we use to make those things. I'm going to leave this up because I'm actually going to give you guys like a page that we can use when we're thinking about stuff. We should know most of these things. The bottom one, I've decided we're not going to do, mostly because we need the time, and I've never seen it show up on the final anyway, so we're going to not do the bottom one. I just didn't reprint the page. So I'm going to give you guys these, and if you want to have them in your notebooks, go for it. If you just want to kind of look at them, whatever you need with them, valid. But I'm going to give you these. These are like the parent tables and kind of the parent function, and also where the A, H, and K are in the transformation form of that specific function, as opposed to it being kind of generic guy up here. There we go. We have that. So we are starting tomorrow going to graph a bazillion things, working our way up towards making those piecewise functions where it has like chunky pieces. We got to there, and I'm thrilled with that.
I am not after school today too.
Yes, I will be here until 3:30.
I talked